When an AI gives you an answer, it can feel, well, kind of like magic, right? Like you're talking to this super intelligent being. But what if I told you that's not really what's happening at all? The big secret is that AI, especially machine learning, isn't about knowing things for sure. It's really about calculating confidence. It's about making the best possible guess it can with the data it has. So, how does it actually make a decision?
And that brings us to the big question we're going to dig into. When a model spits out a prediction, what does its confidence level actually mean? How sure is it really? This quote right here, it just hits the nail on the head. It's not about certainty. It is all about probability. The language that machines use to make sense of our messy, unpredictable world, well, it's the language of chance. So here's how we're going to break it down. First, we'll look at what a prediction score actually is. Then, we'll explore the different ways of thinking about probability and the super important step of turning a forecast into an action. After that, we'll dive into the two main kinds of uncertainty. And we'll finish up with how we can actually take control of the whole decision-making process.
Okay, first things first, let's tackle the biggest misconception right out of the gate. The numbers an AI gives you, they are not facts about the future. They're confidence scores.
So let's take a business example. A model might say, hey, this customer has a 78% chance of churning, of leaving. Now, pay close attention to the wording there. It's not stating a future fact. It's really a statement about the model's own calculation. It's telling you its confidence level based on all the patterns it's seen before.
Which, of course, leads you to wonder, if a model is, say, 99% confident, does that mean it's definitely right? You might be surprised by the answer.
Yeah, the answer is a big fat no. It's totally possible for a prediction with 99% confidence to be flat out wrong, while another one that's only at, say, 53% turns out to be spot on. That score is just a measure of the model's internal certainty, not some kind of guarantee of real-world truth.
Now, to really get this, we have to talk about something that's kind of surprising. Even the experts don't totally agree on one single definition of probability. There are two major schools of thought, and they give us two totally different ways of looking at this.
So, on one side, you've got the frequentists. They see probability as something objective, based on how often something happens over the long run. Flip a coin a million times, it's going to land on heads about half the time. Pretty straightforward. But then you have the Bayesians. For them, probability is more like a subjective belief. You start with a hunch, an initial idea, and then you update that belief as you get more information. And this Bayesian way of thinking, it's really at the heart of most modern AI, which is always updating its beliefs as it sees more and more data.
All right, so we get it. A prediction is a probability. But so what? A probability by itself doesn't actually do anything. And this brings us to a really crucial distinction: the difference between a forecast and an action. See, a prediction just tells you what might happen. That customer has a 78% chance of leaving. A recommendation, on the other hand, tells you what to do about it. It says, because that customer is likely to leave, maybe you should offer them a 10% discount. One is just an observation, the other is a strategy.
And this analogy? Oh, it's perfect. A prediction is like the weather forecast, saying there's an 80% chance of rain. That's just data. The action, the recommendation, is you deciding to actually grab an umbrella. That's the step that turns a simple probability into a practical real-world decision.
So if these models can never be 100% certain, where does all this uncertainty even come from? Well, it turns out it comes from two very different places.
First up, there's what's called data uncertainty. This is the randomness that's just kind of baked into the world itself. Think about noise in a sensor reading, or just how messy and unpredictable real-world data can be. You can't get rid of this, no matter how much data you throw it at it. It's just part of the system. Right. So even if you had a perfect model, some things in the world are just inherently fuzzy or random. That gap between a nice, clean model and our messy reality, that's where data uncertainty lives. It's the baseline of randomness that no amount of modeling can ever completely erase. Now, the second type is model uncertainty. This comes from the model's own limitations. Maybe it just hasn't seen enough data, or maybe it's not the right kind of model for this particular job. But here's the good news. We can actually reduce this kind of uncertainty by getting more data or building a better model.
This visual is a great way to think about it. The bright areas are where the model is super confident because it's seen tons of data like that before. But the darker, fading areas,
That's where it's getting less sure of itself, basically signaling, hey, I don't have a lot of experience in this zone. This is the kind of uncertainty we can actually work on and try to fix. Okay, now we get to the really cool part, the payoff. We understand prediction scores, we understand uncertainty, so how do we actually use all this knowledge to take control and make smarter decisions? Well, we do it by tuning the decision threshold. Let's use a very serious, very high-stakes example from medicine. Imagine a model that's designed to help doctors screen for cancer. Now, the most important question here isn't about accuracy percentages. It's about something much more human. What is the real-world cost of being wrong? So, by default, a model might just use 50% probability as its cutoff. Anything over 50 is a yes, anything under is a no. But think about it. What about a patient with a 40% score? With that default set in, we'd miss them. And in this case, the cost of a miss, a false negative, is absolutely catastrophic. So the priority isn't to be perfectly accurate. It's to find every single potential case. So we change the rules. We manually lower that decision threshold way down to something like 10%. Now we're flagging anyone with even a small chance so they can get a closer look. Yeah, we'll get more false alarms, but we're doing it to make sure we don't miss a single critical case. And that's the absolute key takeaway here. There is no single best threshold. The right threshold depends entirely on the context and on the real-world consequences. Are you trying to avoid missing a cancer diagnosis, or are you just trying to avoid sending a customer a discount they don't really need? The answer to that question changes everything. So let's just quickly recap the big ideas. We've seen that AI predictions are all about probability, not certainty. We've learned that a prediction just tells you what might happen, but a decision is what you do about it. We've also figured out that uncertainty comes from two places, the data itself and the model's own limits. And most importantly, we now know that we can and absolutely should tune our decision thresholds based on real-world costs and what truly matters. And that really brings us to our final thought. Maybe the goal was never to build a machine that knows everything for certain. Maybe the true goal is to build a tool that understands its own uncertainty. So the next time you get an answer from an AI, don't just ask if it's right. Ask the much more important question. Okay, but what's the cost of being wrong? That question, that's the shift from just using AI to truly reasoning with it. You know, when an AI makes a prediction, like spotting something in a photo, it doesn't just give you the answer. It also tells you how confident it is. And that sounds great, right? I mean, a confident AI seems like a trustworthy AI. But what if I told you that confidence could be hiding a really, really big problem? Okay, so let's get right into it. To really wrap our heads around the problem, we first have to be super clear on what we're even talking about. What exactly is AI confidence? Well, it all comes down to something called a confidence score. It's just a simple number, somewhere between 0 and 1. So if an AI looks at a picture and says, that's a bicycle with a confidence of 0.92, it's basically telling us, hey, I'm 92% sure I got this right. It's the machine's way of showing its work, of communicating its own certainty for that one specific guess. And this isn't just some theory, you know. Developers use this in the real world all the time. For instance, they can set what's called a confidence threshold, something like conf equals 0.5. That's basically an instruction to the AI saying, look, only show me the predictions you're at least 50% sure about. Anything less, just toss it. It's a handy way to filter out the noise. Seems pretty logical. But here is where our whole story takes a really sharp turn. What happens when a model is shouting from the rooftops that it's 99% confident, but that confidence is built on a foundation of completely flawed, biased data? And that, right there, is the question that turns AI confidence from a neat tech feature into a massive ethical headache. So let's take a look at what happens when an AI's confidence doesn't tell the whole story, and, more importantly, how that can have a huge impact on real people's lives. Okay, what you're looking at here isn't a hypothetical. This came from a real tool called Compass, used in the American justice system to predict the risk of reoffending. On the left, you have Dylan Fudgett, who was rated low risk despite a prior conviction. He later got arrested 3 more times. On the right, Bernard Parker was rated high risk, and he went on to have 0 subsequent offenses. The investigation found the tool was twice as likely to falsely label Black defendants as high risk. And this wasn't a one-off. Here's Gregory Lugo, rated as a low risk, who went on to commit another offense, and Mallory Williams, rated as a medium risk, who didn't.
And here's the absolute kicker. The algorithm wasn't even given race as a factor, but because it learned from historical data that already contained decades of human bias, it ended up just replicating those same societal biases. It all comes down to this classic saying from the world of statistics: garbage in, garbage out. It's so simple, but it's the absolute core of the problem. If you feed a machine a diet of data that's full of our own historical prejudices and flaws, the machine will learn those flaws perfectly. It just becomes a mirror, showing us the very biases we're trying to escape.
And this isn't about fixing one simple mistake. Bias can creep into the system at every single stage. You can see it here, from the moment data is created, to how it's sampled, to how the model is built, and even how it's evaluated and used in the real world. It's a systemic problem through and through.
And this issue is everywhere. Seriously, Amazon had to scrap a hiring tool because it learned from past hiring data to penalize resumes that mention the word women's. In healthcare, an algorithm thought Black patients were healthier simply because they spent less money on care, completely missing the fact that this was due to barriers to access, not better health. It's deeply woven into the fabric of our digital world. So, if we can't trust an AI's confidence on its own, how in the world can we ever know if it's reliable? Is there a better way to measure this? Thankfully, yes, there is, and the magic word is calibration. A model is well calibrated if its confidence actually matches its real-world performance. So if a perfectly calibrated AI tells you it's 80% confident about a bunch of predictions, it will be correct about 80% of the time. Its talk matches its walk. That is the real goal. Now, it's really easy to mix up calibration with accuracy, but they are totally different things. Accuracy tells you how often the model is right overall. It's final grade, if you will. Calibration, on the other hand, tells you if the model knows when it's right. You could have a model that's 95% accurate, which sounds amazing, but if it's 99% confident on all its predictions, including the ones it gets wrong, it's poorly calibrated, and you just can't trust it when the stakes are hot. Okay, so calibration sounds like the perfect solution, right? Why don't we just use it for everything? Well, there's been a massive challenge. Measuring calibration is really, really hard. And that's because real-world data is almost never neat and tidy. It's messy, it's incomplete, and a lot of it is unlabeled. This leads to a huge headache that researchers call positive unlabeled learning, or PU learning. Imagine you're training an AI to spot pictures of cats. You've got a million photos you know for a fact have cats in them. That's your positive data. But then you have another 10 million photos that are just a giant unlabeled pile. Some are dogs, some are cars, some might even be other cats you missed. You don't have a clean set of not cat photos, so how can you possibly check your model's confidence when you don't even know what it's getting wrong? Well, this is where a truly major breakthrough comes into play. A team of researchers developed a brand new method. They call it PuESE, and it's designed to do exactly that. It's a tool that can accurately measure an AI's calibration error, even when it's working with that messy, incomplete, real-world data we see everywhere. Now, to get just how big of a deal this is, we're going to geek out for just 1 second. For years, with perfect, clean, fully labeled data, researchers knew the mathematical limit for how accurately you could measure calibration. This number here represents that limit. Think of it as the gold standard, the best possible score you could ever hope to achieve, but only in a perfect world. Now, here's the amazing part. This new PECE method, working with all that messy, unlabeled real-world data, achieves the exact same gold standard score. It completely closes the gap. This means we no longer need perfect data to perfectly measure an AI's reliability. It's an incredible achievement. Let's be clear, this is a huge deal. That massive technical barrier, that excuse that we couldn't properly audit AI for fairness because our data just wasn't good enough, well, that barrier has just been completely smashed. We now have the tools to do the job right. So, what does a breakthrough like this actually mean for all of us? What does it mean for building a future where we can actually trust our AI? It means everything comes full circle. This really advanced, kind of nerdy mathematical research gives us a direct, practical tool to fix the very real problems we saw in courtrooms, in hiring, and in healthcare. We can now go back to those biased systems and ask a much smarter question. Not just how confident are you, but is your confidence actually calibrated and reliable? At the end of the day, an AI is just a mirror. It reflects the data we show it, and we've seen how it can reflect our deepest hidden biases with terrifying confidence. The question now is for us, armed with these new tools and a much deeper understanding, how do we make sure that mirror reflects not the worst parts of our history, but the very best of our hopes for a fair future?
We're always hearing about these incredible things AI can do, right? From spotting diseases to driving our cars. It really feels like it's unstoppable. But what happens when these super smart systems run into something completely new, something they've never seen before? Well, they often don't just get it wrong, they can fail, and fail spectacularly. This right here is AI's biggest blind spot, and we're about to dive into exactly why that is.
And this quote just hits the nail on the head. The single biggest threat to making AI reliable isn't some deep, hidden flaw in the tech itself. Nope, it's how it deals with the unexpected. These unexpected moments are what we call edge cases, and they are the exact problem we're going to unpack in this explainer. And just so we're clear, we're not talking about minor glitches here. We are talking about really high-stakes stuff. I mean, an AI can be trained on millions of miles of perfect road data, but one weirdly placed temporary sign can throw it into total confusion. It can look at thousands of medical scans and be right every time, but then completely miss that one in a million condition. These failures are critical, and they happen in the moments that matter most. So, to really get this, we're going to peel it back like an onion, layer by layer. We'll kick things off with the big problem of edge cases. Then we'll dive into the more technical side, the known versus the unknown. After that, we'll check out how researchers are trying to categorize all this, and then, the important part, we'll look at the solutions and why this is so crucial for the future of AI. All right, let's jump in. First up, the problem itself. What exactly are these blind spots? And what is it that makes them so incredibly dangerous? The key here is that combination of words, low frequency and high impact. See, an edge case might be super rare, but the consequences when it happens, they can be massive. It's not just some random outlier in the data. It's a whole scenario the AI was never prepared for, because it lives completely outside the clean, predictable world of its training.
So why are even our best, most sophisticated models so brittle? Well, it pretty much boils down to three things. First, the data they learn from is always biased towards what's common and typical. Second, the real world is messy. It's always changing, which researchers call a distribution shift. But maybe the scariest reason is that these AI models are often wildly overconfident. They literally don't know what they don't know, so they'll spit out a completely wrong answer with the same level of certainty as a right one.
Okay, so let's get a bit more scientific here. We're going to shift from just saying edge cases to the more precise technical language that researchers actually use to tackle this.
This right here frames the problem perfectly. Think of it like this. AI is traditionally built for a closed world. It assumes everything it's going to see in the wild will look pretty much like the stuff it trained on. We call that in-distribution, or ID for short. But the real world, that's an open world. It's filled with new, novel, totally unexpected things. That's out of distribution, or OOD data. And that is exactly where all the dangerous edge cases are lurking.
Now, even within that big open world, there are different kinds of changes. The first is what's called a covariate shift. This is when the appearance changes, but not the actual thing. So imagine a cat sitting in bright sunshine versus that same cat hiding in a dark shadow. It looks different, sure, but it's still a cat. A good, robust model should be able to handle this. But the second type, this one is much more critical. It's a semantic shift. This is where the meaning itself is brand new. A model that was trained to identify cats, dogs, and fish is suddenly shown a picture of a car. That's not just a different-looking cat. It is a totally new category that the model has never, ever seen before. And that right there is the whole game. While an AI needs to be tough enough to handle those covariate shifts, like our cat in the shadows, it absolutely must be able to spot the semantic shifts. It has to be able to raise a flag and say, "Whoa, I have no idea what this is," instead of just confidently guessing that a car is a weird-looking dog. That's the core mission of OOD detection.
So with this messy universe of unknowns, how do researchers even begin to organize it? Well, they've come up with a framework to try and put all these different flavors of the problem into some kind of order. This whole framework basically breaks down into three related challenges. You've got anomaly detection, which is all about spotting when something deviates from a super specific baseline of normal. Think of a machine on an assembly line looking for one cracked bottle among thousands of perfect ones. Then there's novelty detection. This is about spotting entirely new types of things, like a Mars rover finding a kind of rock it's never been shown before. And finally, open set recognition. That's kind of the whole shebang. It has to do its normal job of classifying things it knows and be smart enough to reject things it doesn't.
They all ask slightly different questions, but they're all focused on one thing: dealing with the unexpected. Okay, so we've defined the problem, we've categorized it. Now for the most important question: what are we actually doing about it? Let's take a look at the toolbox people are using to build more robust AI. So there's no single magic bullet here. It's really a continuous cycle of improvement. It all starts before you even train the model by trying to find diverse data that includes some of those rare events. Then, during training, use cool tricks like data augmentation to basically create fake edge cases for the model to learn from. Once the AI is out in the real world, you build a safety net. You keep a human in the loop for the really critical decisions. And the job is never, ever done. You have to constantly monitor the model, update it, and use tools that help explain why it failed, so you can feed those lessons right back into the start of the cycle.
And let's be very clear, these are not just theoretical academic problems. The consequences are incredibly real. In healthcare, it could mean the difference between a life-saving diagnosis and a fatal delay. For self-driving cars, it's the razor's edge between a safe trip home and a tragic accident.
Because in fields like these, it only takes one single failure, one misidentified pedestrian, one missed tumor. That is all it takes to cause irreversible harm and completely shatter all the trust that was built from a million correct predictions. And this brings us to this core dilemma, what's often called the long tail problem. This is why you can't just say, oh, we'll just collect more data. While any one specific edge case is rare, the number of possible weird things that can happen is basically infinite. So this forces a huge shift in how we think about AI. We have to move away from trying to train for every possibility and instead focus on designing systems that are resilient when they inevitably face something new. So this all brings us to the big picture. You know, solving this edge case problem isn't just about making slightly better models. It's about building an AI that we can actually trust with our future. I think this quote just sums up our entire journey today perfectly. You can prove a model is competent on all the everyday boring stuff, but our trust in that model, that is defined entirely by how it behaves in those few rare, unexpected moments. That is the real frontier. What this means is that the very goal of AI development is evolving. For years, the big challenge was generalization, making sure a model could recognize a dog, whether it was in bright light or shadow. And that's still important for sure. But the new frontier, the other side of the coin, is detection. Building a model that knows when it's not seeing a dog and has the humility to admit it. And getting there, well, it's going to take progress everywhere. We need models that actually understand context, not just recognize patterns. We need tools that let us peek inside the AI's brain to see how it's making decisions. And of course, we need better data. And maybe most importantly, better systems for human oversight and real accountability. All of this incredible work is pushing us towards teaching our machines how to expect the unexpected. But it leaves us with one final profound question. As we push AI deeper and deeper into our lives, into more complex situations, how do you possibly prepare it for challenges that aren't just rare, but are truly, completely unimaginable? That, right there, is the challenge that's going to define the next decade of AI.